in this lesson, we're going to be talking about how we can find the probability generating function for a Poisson distribution. So I'm going to be making use of this example here to demonstrate to you how we can do that. So let's get into it. The question says, the random variable x follows a Poisson distribution such that x follows a Poisson distribution of mean lambda. So on A, using the fact that the sum from r is equal to 0 to infinity of terms of the form x to the r over r factorial is equal to e to the x, show that the probability generating function for a Poisson distribution is given by g x of t equal to e to the lambda of t minus 1. And on B, prove that the mean and variance are both lambda. Okay, so let's get to the solution, and we're starting with part A. Now on part A, they want us to find the probability generating function and to show that it comes down to this. Now we know already that probabilities for a Poisson distribution are calculated as e to the minus lambda, and that's of lambda to the power r over r factorial. And we also know that for a probability generating function, it is found generally by the sum for all values of x of the probability px to x times t to the power of x. So this is what we're going to use to find the PGF for a Poisson distribution. Alright, so here I'm going to say for a Poisson distribution, gx of t should be equal to the sum, and that's from r is equal to 0, and we know that a Poisson distribution can go up to infinity, and that's off for the probabilities. I'm going to make use of this, that's e to the minus lambda of lambda to the r over r factorial, and then that's times the t function, t to the r in this case. Alright, so here I'm going to be having the sum from r is equal to 0 up to infinity, and that's off. Here I'm going to combine lambda to the power r and t to the power of r, so that we get lambda t to the power of r, and that's over r factorial, and that's times e to the minus lambda. Now in the question, they said we should use the fact that the sum from r is equal to 0 to infinity of x to the power of r over r factorial is equal to e to the power of x. So we're going to make use of that fact here. So I'm going to say, since the sum from r is equal to 0 to infinity of x to the power of r over r factorial is equal to e to the x, so we can therefore say g of t is e to the power of, in place of x, there is lambda t, so it's e to the power of lambda t, and that's of e to the minus lambda like we have here. So we can simplify it to get e to the power of, adding up the powers, that's lambda t minus lambda, which is equal to e to the power of, factoring out the lambda, that's lambda of t minus 1. And this is what they want us to show, so I'll say hence shown. So that's how we do it for that first part. Let's go on to part B. Now on part B, they say, prove that the mean and variance are both lambda. So here we're going to start by finding the mean, which is the expectation. And we know that expectation is found by g dash of 1. So this is the result we are going to make use of. Alright, so here, since we got g of t coming out as, we got it as e to the power of lambda of t minus 1, which is the same as, taking it back a little, e to the power of lambda t times e to the power of minus lambda. So we can find g dash of t, which means we are differentiating this. Okay, so e to the power of minus lambda is a constant, and differentiating e to the power of lambda t with respect to t, we get lambda of e to the power of lambda t. So therefore, g dash of 1 means we're substituting 1 for t, so we'll be having e to the power of minus lambda times lambda of e to the lambda. And we can simplify this a little bit more. Here we've got the lambda, and that's e to the power of minus lambda plus this lambda, which eventually gives us e to the power of 0. So we just get lambda eventually. So therefore, we have proved that the expectation, which is found by g dash of 1, is lambda. So hence shown. Now we can look for the variance. So here I'm saying for variance, we will need to find g double dash of t. And for g double dash of t, since we got right above g dash of t as this, it means we will only need to differentiate this. So already we've got the constants, lambda and e to the power of minus lambda. So that's lambda and e to the minus lambda. And differentiating e to the power of lambda t, we get lambda of e to the lambda t. So let's simplify this. So this is going to be lambda squared of e to the minus lambda, and that's plus lambda t. And for g double dash of 1, that'll be lambda squared of e to the power of, and for the power we'll be having minus lambda plus lambda of 1, which is just minus lambda plus lambda, so that gives us 0. So we are getting lambda squared for g double dash of 1. So we know that variance is calculated as g double dash of 1 plus g dash of 1 minus g dash of 1 squared. Alright, so here for g double dash of 1, we have found it as lambda squared, and it's plus g dash of 1, that's the expectation. We got that right above as lambda, and it's minus g dash of 1 squared, which is lambda squared. So eventually, lambda squared minus lambda squared is 0, and we are left with the variance coming out as lambda. So again, we are saying that the variance is lambda, so we can say hence shown. So we have thus proved that the expectation and variance are both lambda. And now, as a matter of principle, the main takeaway here is that if x has a Poisson distribution such that x follows a Poisson distribution of mean lambda, then the probability generating function for x is given by g of t equal to e to the lambda of t minus 1.